Welcome back. So now we will go in a little bit more mathematical details about narrowband fading channels. So the first equation is the one that you've seen before, right? Where you have a received signal, which is a superposition of paths, each with their own delay, amplitude, and phase. And this phase varies very quickly. Now we invoke the narrowband assumption, which means that all of these delays are the same here. So that I can remove these delays, which means that I can pull out this u of t from the summation. Okay, so then I have this part, and then the channel is just this. So what I now get is the sum of a bunch of complex numbers, and together I will call them beta. Okay, so this is the complex baseband channel, and this is just one complex number that changes over time. And well, you can already imagine that when n is large, you can invoke the law of large numbers, and then you will end up with a Gaussian random variable, but that will happen later. Good, so then if we put all of these things together, you will see something like this. You will have the, sorry, what happened here? The transmit signal with a certain power. Then we multiply with path loss, so this is something that of course will reduce power, shadowing, fading. Then we add noise, and then we have our output signal. And then when we look at the power of this received signal, it would look something that could be like this, right? So when you move over short distances, and short is with respect to, well, a few wavelengths, you will see that the power can fluctuate a lot. And this is really due to this fading effect. And this average value here, this is due to path loss plus shadowing. Okay, so this is the 0 dB level is the value due to path loss and shadowing, and then you have variations around this due to fading. So then the main thing that we need to do now is look at the model for beta of t. So what is the statistical model for beta of t? Well, part of this is easy. The expected power of beta of t should be the power due to path loss and shadowing, right? So the expected value of the power of beta of t, so the amplitude of beta of t squared, will be path loss, which is this guy here, times the shadowing. Okay, and recall the shadowing in the dB domain has a Gaussian distribution. In the linear scale, it is a log normal random variable. All right, so but now that's just the power. So we also need to talk about the distribution and the autocorrelation. So the distribution is one aspect. So this tells you how you can generate this channel by drawing samples. The autocorrelation tells you how quickly this channel changes over time. And this relates to the Doppler shift, which in turn depends on the mobility, so the speed and the wavelength. So there are two common models for the distribution, the Rayleigh fading and the Ricean fading, although there are many other cases that exist. So we'll cover those next. Good, so first of all, the Rayleigh fading model. The Rayleigh fading model assumes that there's a transmitter, let's say a remote transmitter here. There's a receiver here moving in some environment, and this is an artificial environment with many objects in the environment. So these are scattering objects. And they're all on a ring around this receiver. So it is very artificial, but it will allow you to get some closed form expression. And now, if you have a large number of these scattering objects, you can apply the central limit theorem without any dominant path. So that means there's no line of sight path from the transmitter to the receiver. And then this tells you, as I already mentioned before, that beta of t will be a complex Gaussian random variable. So in other words, beta of t will be complex Gaussian zero mean variance 2 sigma squared, right? So, and this means that the real and imaginary part have both zero mean and variance sigma squared. And then this variance is due to path loss and shadowing. right? And this becomes, so this 2 sigma squared, this corresponds to this equation here. Now, when a channel is Gaussian, there's also a known distribution for the envelope of this channel, so this is the absolute value, and this is called the Rayleigh distribution. There's also a known value for beta t squared. Okay, this has an exponential distribution. Okay. So the Rayleigh fading model has three distributions, right? Gaussian for the channel, Rayleigh for the absolute value or the envelope, and then exponential distribution for the power. And the figure here shows the Rayleigh density, the cumulative density, as well as the expressions for both of these. And as you can see, the Rayleigh density is only defined for non-negative values, right? Because it's an amplitude. The exponential distribution, so if I could do beta t squared, and then the distribution of this, exponential distribution would look something like this. It's a rough sketch, but if you want to know more about these distributions, a good resource is Wikipedia, actually. Now here, so we made one important assumption, which is that there's no line of sight path. So there's a variation of this model where there is a line of sight path, and that's a Ricean model. Before we do that, it's maybe instructive to think about how we would generate this path loss shadowing and Rayleigh fading in MATLAB. And with this slide, I try to explain this to some extent. So first of all, you have to decide on all your channel parameters as well as the transmit power. So that's the first part. Second part is you generate the path loss. The path loss is given by this expression, right? So you have to decide this k factor, the reference distance, typically 1 meter, the distance between transmitter and receiver, and the path loss exponent gamma. And this is, of course, the power averaged in the dB domain over the shadowing, as well as the fading in the linear domain. Okay, so then what we end up with, this is the received power due to path loss only, is the transmit power times the path loss. And of course, this is strictly less than the transmit power, right? Because you lose power over this distance. And this highlighted red text, I think you should think about as why this is true. Then we generate shadowing. And the way that we generate shadowing is by a Gaussian random variable in the dB domain. Then we convert this shadowing to linear scale. So this is what this is doing. And then the received power after path loss and shadowing is given by this expression. And now you can go from this one to this one by taking an expectation in the dB domain. And that's what this statement is saying. Fourth step is you generate multipath fading power. And recall that the power of the multipath fading is an exponential random variable. So you can write this as this. So you generate an exponential random variable. And then the received power is the transmit power, path loss, shadowing, times this exponential random variable. And this is power, right? This is not a channel. In order to generate the channel, this is the last part, you have this shadowing variance. So this is 2 sigma squared, which depends on the path loss and shadowing. And then you just generate beta as a complex Gaussian random variable based on that. Good, so let's see how this would look like in a kind of MATLAB pseudocode. Here I generate 200 realizations. I choose a value of k. I probably computed this somehow. Reference distance of 1 meter, distance of 150 meter. Maybe here it's also important to note that you should keep your units consistent. The units are your friends and they will make sure that your results make sense. Path loss exponent of 2, that's gamma here. Then my sigma squared psi in the dB domain I set to 4. Transmit power of 1 milliwatt. Then I compute this path loss, right? Which is the expression here. Then I compute shadowing as a Gaussian random variable. This is this part here. I convert the shadowing to linear scale. I do this here. I generate a realization of fast fading as an exponential random variable. And this is a built-in MATLAB function. I generate n realizations of the fast fading. And then I have in step 12 my received power, which is a vector of 200 numbers for this given transmit power, given path loss, and given shadowing, and different values of the fast fading. And then I make a plot of this. And I hope in the next slide this will be shown. No. Okay, maybe not. But then you can try this at home. Good, this is an example of the same thing. I'll skip that. Right, so there is another model called the Ricean fading, where there is a line of sight path between the transmitter and the receiver. Okay, so there's one dominant path, which has, and also, of course, there's one dominant path plus many scatterers, and then we say that the amplitude of the channel has a so-called Ricean distribution. Let's look in more detail what this looks like. So the channel has two parts. There is a line of sight path. Here, this is the line of sight. And then we have the remaining paths which come from the scatters. And we know already this has a Rayleigh distribution. Now, of course, we know that the expectation of beta t squared is equal to transmit power times path loss, times path loss times shadowing. So this here is given to us. And since now we add this line of sight path, we need to split this total power part to the line of sight, part to the non-line of sight paths. So the way that we do this is we say that the line of sight path has a power s squared. The non-line of sight path has a power 2 sigma squared. And then the sum of those, s squared plus 2 sigma squared, will be equal to this total power, pt times path loss times shadowing. So you can choose how much power you want to give to the line of sight and to the non-line of sight, and the ratio between these two is the k factor. So this means that when k is equal to 0, all the power is in the non-line of sight, and we have the pure Rayleigh fading model. And when k goes to infinity, we have a pure line of sight channel, and then we basically have an additive wide Gaussian noise channel. I can now plot this Ricean distribution for different values of k, and this is what it looks like. So in this case, the total power due to path loss and shadowing was 5. And then when I choose k equal to 0, I have a Ricean distribution. When the k is larger, I have a distribution that becomes more peaky around this mean value. Good, so these are the two most common models for narrowband fading, the Rayleigh distribution and the Ricean distribution. So here is an example of how you would generate that. Again, we want to generate 200 realizations. Let's say the average power due to path loss and shadowing is given by 0.01. I just put arbitrary value here. The Ricean k factor is 500, and this will be one of the figures below. Based on this k factor, I can compute sigma squared, which is the, this is the Rayleigh part. I can also then compute s squared, which is the line of sight part, by dividing the power. And then I generate the corresponding channels. For the line of sight part, it's easy. This is the amplitude, and I put a random phase, because this phase depends on the delay between the transmitter and the receiver, so I just put it random. And then there's a non-line of sight part where I give the power of the Rayleigh part. The amplitude corresponds to the Rayleigh part, and then I have a complex Gaussian random variable. Rand and rand are built-in functions in MATLAB. And then this gives me the total channel. I can then compute the power of this channel and make a histogram. And this histogram is what is shown here. And here you see for k equal to 0, right? This is the standard Rayleigh fading, k equal to 5 and k equal to 500. And you see that the received power becomes very peaky around the mean. And for all of these cases, the mean will be the same value. The mean will be 0.01. I think it's time for another break. See you soon.